Hello everyone and welcome to CP-31 Sheet Solutions. This is Vibhaas from TLE Eliminators, and today we'll be discussing the 10th problem of the 1600 rated sheet, equal frequencies. So let's go ahead and open the TLE Eliminators sheet and we see the problem equal frequencies. Let's go ahead and quickly read the question and then we'll dive right into the solution. Okay. Problem C, equal frequencies. Let's call a string balanced if all the characters that are present in it appear the same number of times. For example, coder, appal, and TTTTTTT are balanced, while wow wow and Codeforces are not. We can see this because coder, each element appears exactly once. As you can see, C appears once, O appears once, D appears once, and so on. Similarly, in the string APPALL, we see that A appears twice, P appears twice, L appears twice. And for this last string, T appears 7 or 6 times, right? T appears 7 times. Right. Meanwhile, in wow wow, W appears 4 times and O appears 2 times, so it's not balanced, right? Okay, so we understood the meaning of balance. You're given a string S of length n consisting of lowercase English characters. Find a balanced string T of the same length n consisting of lowercase English characters that is different from S in as few positions as possible. Okay, so we need to find a string which is different in as few positions as possible, but it is balanced. Okay, so our n goes up to 10 to the power 5 and sum of n also is up to 10 to the power 5, and we have to output the number of positions where they can differ as well as the balance string. So that's the output expected. So before even starting the question, we should first analyze the time complexity. So we can write time complexity expected, right? So since it's given expected, yeah, since it's given that n goes up to 10 power 5, we expect some solution on the order of O of n, O of n log n, or similar, right? So initially our brain has some thoughts like this, that we need a solution of about this time complexity, and these would be valid. Solutions which are n square or more will not be valid. All right. Now let us understand how to break down this problem. So if you directly approach this problem, it might seem a bit bewildering because there are many possible balance strings which can, go here, and how will you compare with all of them? But one of the things you can realize pretty quickly is that um, we can think about what is the frequency of each character. All right. So what is the frequency of each character? All right. So this is the thing which should come to your mind, that let's say our target string, let us imagine a target string and then think about the properties of this target string. So like the answer string, right? So let's say we have some string um a b c b b c d, right? So this is our string, and let's say the string which minimizes the number of let's say the string which minimizes the number of changes. Let's say there is some string which minimizes like the number of changes which occur, but it's a balanced string, right? As you can see, this string is unbalanced. So we can think of what will be the frequency of each character. All right. So let's say um, all the characters have a frequency of 2, right? Will that be a possible solution to this? And we can see no, because the total number of characters itself is 7, right? N equals 7. So we already know that that's not a possible solution. Similarly, for many other cases, we can show that it's not a possible solution simply because the frequency of each character must at least divide n. Okay, so the frequency of each character must at least divide n. Frequency of each character must divide n. Okay, so that's one interesting observation which we get when we look at the strings. Okay. Okay. So for example, instead of having 7 characters, let's add a 8th character as well. Let's say there was a EO here. All right. Now this string, if you observe this string, now we can have a possible frequency of each character as 2. For example, AA, BB, CC, DD, right? This is one possible string which we can have. Or the one which minimizes changes, we could say, since we already have DD, we'll keep these same. Similarly, we already have BB, we'll keep these same, right? Now for the remaining, we can change it to anything we want. So let's make this AA. A over here will be same. And then let's make this BB. Sorry, CC. CC, right? So we have seen the first observation that frequency of each character must divide n. And also we have an interesting constraint we can see is that there are only 26 characters in the English alphabet, right? There are only 26 characters in the English alphabet, and this is a good constraint. This is a very good and limiting constraint. Okay, and limiting constraint. Now the reason for this is let's say our final answer string, our final answer has k unique characters. Okay, so let's say our final answer has k unique characters. Then we have this nice equation that k times n, k times frequency of each character, k times f, is equal to n, right? And this is why we can say that the frequency must divide n, also the k must divide n. All right. So, and also we can say another way we can write it is frequency of each character will be n divided by k, right? If there are k characters, then frequency of each character must be n divided by k. And these are some simple observations we made just by noting down the lengths of the characters and taking into account that each character repeats for the same frequency, right? Length of the string and each character repeats for the same frequency. So what observation does this help us arrive at? So right now let us just focus on finding the minimum number of changes required, right? Later we will try to construct the string, but first let us try to find the minimum number of changes required. Okay, so let's say let's say our answer string, okay, answer string has exactly k unique characters. Okay, so that's what we defined as definition of k. Let's say our answer string has exactly k unique characters. Then what are the observations we can make? Okay, what are the observations we can make? We can say that frequency for each character should be n divided by k. Correct? Frequency for each character should be n divided by k. So how do we minimize changes? How to minimize changes if we know this, right? How to minimize the changes? Let us assume that our current string has some frequencies. Okay, our current string has some frequencies. So let us give some numbers for an example so it becomes clear. Let's just do an example. So let's say k unique characters, let's say k is 4 and let's say f is 3. Okay, so total n will be 12, right? So let's say we want 4 characters each with frequency of 3 for our answer, and we need to minimize the number of changes, right? So let us imagine a frequency map. Okay, so let's say the character A, it appears 6 times, character B, it appears 3 times, character C, it appears 2 times, and character D appears 1 time. As you can see in the original string, this is the frequency of the original string, and n equals 12, so the sum of all these frequencies will be 12, right? Now our goal is to make all the frequencies equal to 3. Correct? All the frequencies should be equal to 3. So what we can observe is in that original frequency map, the 4 highest characters 4 highest characters, they will be so 3 of these A characters will be untouched. Similarly, 3 of these B characters will be untouched. These 2 of these C characters will be untouched, and one of these D characters will be untouched, right? And the remaining characters need to be changed accordingly. Or let me just change the frequency map slightly to make a better point. So let's say we had B has 2 occurrences, C has again 2 occurrences, or C has 1 occurrence, D has 1 occurrence, and let's say, okay, D has 1 occurrence and E has 1 occurrence, right? So let this be the frequency map. So our original string can be something like AAA, BB, CC, DE, right? Something like this. Now we want everything to have frequency of 3. So what we can say is these A's, the first 3 A's, we'll leave them untouched. Similarly, we'll leave these 2 B's untouched, these 2 C's untouched, and this D untouched, right? And then the remaining, we can make this into a D. We can make this into a D. We can make this into a B and make this into a C, and then the frequency of everything will be 3. So basically, in the frequency map, the highest k elements, we will leave their values untouched, right? We will leave basically minimum of frequency target, like the target frequency, which is n by k. So minimum of n by k times the frequency of the character for the first k for the highest k frequency characters. These will be the untouched ones or unchanged ones. Okay. So now that we have counted how many characters will be unchanged, the remaining characters must be changed, right? So the number of changed characters, therefore changed characters will be equal to simply n minus the number of changed characters will be equal to simply n minus unchanged, right? Okay, so from this we can see quite simply how to find your target k, right? Exactly k unique characters, because the possible values of k are only from 1 to 26, right? Because the English alphabet has anywhere between 1 to 26 characters. So if we have exactly 1 to 26 unique characters, we can figure out what is the k which minimizes our change characters, right? So we can write a pseudocode like this. Pseudocode for k from 1 to 26. For k from 1 to 26, add, so let the unchanged characters equal 0. Then for top k elements in frequency map, we can say unchanged will be added with the minimum of frequency of that character or n by k, right? Whichever is lesser, right? Because if you see here, A appears 6 times, but it is limited by n by k, so this becomes 3. Meanwhile, B appears 2 times, so it's limited by 2, the number of times it appears, so this will be 2 itself, right? These will be the number of unchanged characters. So now changed will simply be n minus unchanged, right? Changed will simply be n minus unchanged. And we can choose the k with minimum value. We did this loop, right? So with minimum value of unchanged, right? The maximum time complexity for this, as you can see, will be about k square, right? Because we're going through a map and k goes from 1 to 26. So the time complexity for this will be, or we're using a map, so depending on whether it's an ordered map or unordered map, it might change, or whether you use an array as well. But yeah, the time complexity for this can be written in big O of k squared. We have found in big O of k squared, we have figured out what is the k number of unique characters, which minimizes the number of changes. Okay, so this finishes part 1 of the problem, right? This finishes part 1, which is finding the minimum changes, right? So we have already found this value, which is the minimum changes required. Now what we need to do is simply find, we have to construct the string, right? We have to construct the string. So now while constructing the string, we just need to keep in mind that we know the frequency required for each character. So every character which has higher frequency, we will just set the first frequency or first three in this example. We will leave unchanged, and remaining can be changed to whatever we want. Similarly, these we will leave unchanged, and remaining characters will be changed to fit whatever is needed, right? So what we can do to construct the string is for the following: how to construct the string. So we know that we have k unique characters, and we also know that those characters are the ones with the highest frequency, right? So we will make a map to keep track of used characters, right? Of used characters. And what will the map contain? The map will be basically map of character to count, and it will be basically A must appear 3 times, B must appear 3 times, C must appear 3 times, D must appear 3 times, right? And what we will do is we'll go through our original string, right? Go through the original string, and every time we find A, for example, we can do map of A minus minus, right? Similarly, every time we find B, we can do map of B minus minus, and so on. And basically what this is saying is that this position is an unchanged position and we should not touch it, right? And in our answer string, we can set that to A. So let us make a different answer string and we'll set that to like A, meaning that this A is unchanged, and we can set that in our answer. Similarly, in the answer string, we can set that to B, and so on, right? Now, once this process is done, there will still be some characters remaining, right? Process is done. The unchanged characters are fixed. The unchanged characters. So this is mostly implementation. That's why I'm telling it directly. There's not much intuition, more like just implementation skills. So the unchanged characters fixed, right? Now only the changed characters we need to care about. And for those, we'll just see the map, right? The map will have the number of remaining characters. So for example, if all the A's are used up, it will be 0. All the B's are used up, it will be 0. C1 will be remaining. Let's say D, 3 are remaining, something like this, right? So these need to be filled now. And we will go through our string of answers, and fill the remaining characters, right? It does not matter what order we do it in, because a change is a change no matter where you do it. So we'll fill the remaining characters. Okay, so that's it. That's the whole solution. We'll put part 1 and part 2 together. In part 2, the time complexity will be big O of n to go through each character, and if you use a map, then it will be big O of n log c, where c equals 26, right? C equals the number of characters, same as before here. Big O of k squared, again big O of k squared can be written as c squared, because this is also 26 characters. So what is our final time complexity? Our final time complexity, and don't worry if you did not understand this implementation, we'll go through the code just in a minute. It will be big O of c squared plus n times log c, right? Where c equals 26. Since 26 is almost a constant, we can write this as big O of n itself, right? Memory complexity is not much. We're just having some small maps with 26 characters, as well as the big O of n space to store the string itself. So the memory complexity is also big O of n. Okay, let's have a quick look at the code for this. So yeah, let me zoom in a bit. Okay, so in the start, we are inputting n and the string s. And now I want to find the frequencies of each character. So you can either use a map or a vector. It does not matter. You can use map, unordered map, vector, or whatever data structure you use. Even if it's a different language, you can use hash map or whatever. So here I'm finding the first 26 characters. I'm finding their frequencies and I'm sorting it. So this is just giving me the frequency of each character. And it should be sorted with decreasing order. Okay, the maximum frequency should be first. Maximum frequency at top, right? Decreasing order, it should be sorted. Now k is equal to the number of unique characters in the answer, like we discussed. We need to find the k which minimizes the changes. So that is what we call the best k. And the number of changes it has is whatever the changes for the best k, right? So now k equals 1 till 26, we do k plus plus. If k does not divide n, then it's not possible, right? We already showed that k and the frequency must divide n. So we just continue in that case. Now here we set unchanged as 0. And the unchanged gets added with the minimum of the frequency and n by k, like we discussed. If the number of changes over here, number of changed over here is less than the minimum which we found, we can update that minimum, right? We can update the best k and the minimum, and that's what we're doing here. So here we have found the minimum number of changes as well as the best k which achieves this, right? Now our job is to construct this string. So here we're using a map to keep count of how many of each character we have to fill. Okay, so this map will be for each character to the frequency, right? The frequency is n by k, n by best k. So that's what we're doing here. Now we'll make an answer string. Initially each character in the answer string will be a blank character, okay, space. Now we're going to fill the unchanged values. So for each character, if it is there in the map, and it has some frequency, that means that we are left to fill this character. So we can set ans of I equals s of I. Basically we're leaving this character unchanged, right? We're leaving this character unchanged and we can reduce that frequency. Now we need to fill the remaining values, and the remaining values we can fill in any order because the change is still a change. So basically if it's a blank, then only then we'll fill. And what do we do here? I'm just erasing the empty values from the map. Now I take the top element of my map and I set it to that character, and I lower that character's frequency. So that's all. In the first half I am finding the minimum number of changes and the best k which achieves that, and in the second half we are constructing that string. The whole code is big O of c square plus n log c, which is about big O of n itself, right? Because c is the number of characters. All right, that's about it for this question. It's mostly implementation / greedy. Once you understand that number of characters is limited and number of possible frequencies are limited, it's pretty simple to solve this question, I would say. Yeah, that's about it for this question. Thank you. Hope you learned something, and see you in future questions.